Okay, so here's where we put trigonometry to use. This is one of the very most useful branches of mathematics because we see right triangles everywhere in our daily lives. Um, Several professions incorporate trigonometry into their daily work, especially engineering, physics, other sciences. So we're going to do some basic applications of trig here in the next several lessons, and you will see some ways that it can come about and how we can use it. So some of these are classic examples, some of them are a little bit more obscure. The first one says that a ladder is going to be unstable if the angle it makes with the ground is greater than 60. So as you increase the angle, it becomes more vertical, less stable, makes sense. So if a 12-foot ladder is used to reach a window that's 10 feet above the ground, will it be unstable? So what we're checking for is that angle that is down on the ground here. So I'm just going to put a theta in that position. Now that's a new symbol, right? So what we're using there is a variable for an angle, and in geometry and other branches of mathematics, that symbol, which is in word form spelled like this, theta, that is the Greek letter that is used most commonly for a missing angle. It's just a zero with a line through it. Other things that you will commonly see, you will see angle called alpha. So that's written this way. And so if I need a second variable label in my problem, I might use alpha. I'm always going to use theta first, but I might use alpha as a secondary label, kind of like x and y. And if I want a third one, I might even use beta, which is just a b with a curve going past it. So that's beta. Those are the three most common ones that you'll see. Okay, so looking to solve for that angle theta. So now from theta, what is that 10? Is that opposite? Is it adjacent? Is it hypotenuse? So I always want to be labeling this, right? So that's going to be my opposite side. 12 is going to be my hypotenuse, and so I'm thinking OH, that's sine. So I'm going to write sine of theta. I don't know the angle, so I'm leaving it as a variable. Sine of theta equals opposite 10 over hypotenuse 12. Okay, simple enough. So from there, what I want to do is just do an inverse sine so that I can get theta out of that function and by itself. So theta is going to equal inverse sine of that ratio 10/12. And when I do that inverse sine, I'm getting approximately 56.4, which means that that ladder was stable, right? Because it had to be no greater than 60. So I've just proven that it's okay to this point. Now, if I had made that ladder if I had made that ladder go higher up instead of to 10 feet, made it go higher up, then it would have been steeper. Or if the ladder had been less of a length, it would have come to here and been steeper. But it's okay with the dimensions that it's given here. All right, on to the next exercise. And this, each one of these comes up, it's useful for you to set up as much as you can. Try to solve as much as you can on your own and then come back and listen to the solution. So always try to go through a little bit of it at least. So we want to know which trig ratio is involved, and that's why we label the O, the A, and the H. And then we also want to know whether we're using inverse or not, and that's just if we're missing an angle. So in this problem, to determine the height of the tree, loggers will measure the angle of elevation to the top of the tree, and the way they measure it is with this tool called a clinometer. And so that clinometer is basically telling them at what incline am I looking up from horizontal. And so this logger is looking up at a 38-degree angle and sees the top of the tree. So there are tools that actually let you do that. That is not just a guess. So if the logger's eyes are 5 feet 3 inches above the ground and the angle of elevation is 38 when standing 25 feet from the base, determine the height of the tree. All right, so I'm going to put an H here for height of the tree. I don't know it, okay? But what I do know is that this distance between the person and the tree is 25 feet. It's 25 feet on the ground, so it's also 25 feet horizontally from eye to trunk, from eye to tree trunk. So I'm looking at this diagram now, and I've got this here, this 25 next to the 38-degree angle. That's my adjacent side. And the height of the tree is across from the 38-degree angle. That's my opposite side. The hypotenuse is not in play here. So the trig ratio that uses O and A is TOA, that's tangent. And so I'm going to write a tangent equation. Tangent 38 is equal to opposite side H, don't know it yet, adjacent side 25. So the height of this, or the h part of this tree is 25 over times tangent 38. That's my exact answer. So on the calculator, the approximate amount was 19.5. So we're going to go 19 feet 6 inches. Okay. Now that's this part of the tree, but I want to know the whole height of the tree. So since this angle measurement was from the person's eyes, we have to account for his height from his eyes. So we need to add on that 5 feet 3 inches. And that's going to give me 24 feet 9 inches. And if you didn't want to do this conversion, you could do 19.5 and just treat this 5 feet 3 inches as 5.25 feet. That would be okay. You just have to remember that's a quarter of a foot, not 3/10 of a foot. But that can be done either way. So to repeat here, once the diagram is settled, and sometimes you'll have to draw this on your own. It's not always going to be provided. You do still want to be doing that O and A step so that you know exactly which trig function to use, and then you can solve. All right, exercise 3. You can draw your own isosceles triangle. I've got one here already. It's got legs of 14 and base of 10. So I'll put those in, 14, 14, and 10. And so if I want to solve for the vertex angle, that's up here, right? So I can put a theta there because I'm trying to solve for that angle. But as of right now, I don't have a right triangle anywhere. So none of my trig ratios apply unless I have a right triangle. So let's do the isosceles triangle altitude to create a right triangle. Okay, and now I've just split that angle in half, right? So let's use this angle down here. I've already used theta, so I'm going to use alpha this time. And let's say that my altitude is unknown, but the 10 now has been split in half by that altitude. So I have a 5 and a 5 on both sides of there. So let's look at this triangle on the right now and consider, if I'm solving for alpha, which two sides do I have with this 5 and 14? Well, the 5 is adjacent to alpha. 14 is across from the right angle, so that's hypotenuse. So this is going to be a cosine problem if I'm using alpha. Why would I want to solve for alpha? Well, if I know alpha, I can then figure out what this half of the vertex angle is using my 180 sum, and then I can just double it, and I'll know what theta was. So that's the plan. Let's solve for alpha now, and then go up here and get this 1/2 theta in order to know what theta is. So A and H is cosine, so cosine of alpha is equal to adjacent 5 over 14, hypotenuse 14. I don't know the input, so let's change this to an inverse function. Inverse cosine of 5/14. That tells me that alpha is approximately, on the calculator, getting approximately 69 degrees here. Okay, so if that's 69, then this must be 21, because I already have 90, so 21 degrees is remaining. So if this angle is 21, so this 1/2 theta is 21, then theta must be 42. Okay, so sometimes it's easier to solve for a different angle in a triangle and then go back and get the other one that you're looking for. This was one of those cases. All right, exercise 4. A lighthouse in Cape Hatteras, North Carolina, 200 feet above sea level. So I think we should probably put that in. This is 200. And if it spots a boat, the lighthouse spots a boat at an angle of depression, okay, that's a key term that we're going to need to get into here, angle of depression of 28 as shown and drawn in, what is the horizontal distance to the base of the tower? So we want to know this horizontal distance here. I'm going to put an X there. Now let's go back to that angle of depression for a second there. If this person that's standing in the lighthouse looks out on a straight across horizontal path, they're not going to see the boat. They need to adjust their eyes downward in order to see the boat. The amount that they move their eyes down is the angle of depression. Now, this is something that we need to get out there now because it is one of the most commonly misunderstood parts of trig. People think of angle of depression as the angle between the vertical and the line of sight. It is not. It is the amount of it's the adjustment amount right? If you're looking straight across horizontally and now you shift your eyes down to look at the object on the ground, that amount of shift is the angle of depression. All right, so what do we do with that now? Because it's not in the triangle. Well, we have two options. One option is to use this Z formation, this alternate interior pair, and just put the 28 down here. The other option is to complete the right angle at the top and make that into a 62. And the thing is, either way works. Because if I use 28, then 200 is opposite and x is adjacent. If I use 62, then x is opposite and 200 is adjacent. Either way, I have a way to write the equation. I'm going to go off of the 28. I'm going to let the 200 be opposite and let the x be adjacent. So O and A, that's tangent. So tangent 28. And so 200 is opposite, x is adjacent, and when x is on the bottom, we know we can switch it. So x is 200 over tangent 28. And so that is going to give me an approximate calculator answer of 376. Put a label on it, and I am good. You would get exactly the same answer if you did tangent 62 because x would have been on the top and 200 would have been on the bottom, and it would have worked out. All right, so angle of depression is that angle looking down. Well, again, a lot of times you're not going to have the diagram drawn for you, so we need to make sure we know where to put that angle. Okay, last example here, and I know this one's running a little bit long too, but give this one a try. Read through it, do what you can with it, and then I will walk you through it. All right, so another generous problem here with the diagram drawn for you. If I was not given a diagram here, and I saw that this had an observer A and an observer B, I'd probably have 2 points on the ground where they're standing, have the blimp above them, and show that vertical height. And beyond that, I'm going to have to figure stuff out. Now this one has angle of elevation. So that's the opposite of angle of depression. Angle of elevation will always come from the ground and look up. So if somebody looks straight across on the ground, they're going to have to adjust their eyes upward to see the object. So that's the elevation angle. Okay, person at point B is looking upward as well, but they're looking upward at a steeper angle. So what is the distance to the nearest foot that separates the two observers? Now, I could just make that distance D. That's fine. But then I don't have a right triangle. What I'd rather do is have this blimp height be an altitude and make a right angle and let this side of it be x and this side of it be y, solve for x, solve for y, and then add them together to get D. I hope that makes sense to everybody. It's easier to use right triangles than non-right triangles as of now. Okay, so if I want to use the 24-degree side, let's set this up. This 1,150, that's my opposite side from 24. The x is my adjacent side, and so that's tangent. I'm going to go tangent 24 equals 1150 over x. So x is on the bottom, switch it up, 1150 over tangent 24. And that comes out to about 2583. You can confirm that for yourself on your calculator. Then I go to the other side, and now I'm looking from the 38-degree angle. Well, 1150 is still opposite. Y is still adjacent, so let's solve that one now. It's another tangent. Tangent 38 equals 1150 for opposite over y for adjacent, and I can just switch the y and the tangent 38. 1150 over tangent 38. Now tangent 38 is bigger. If I divide by a bigger number, I'm expecting to get a smaller result. And in fact, I do. I get 1472. And if you could think about it, if I'm looking up steeper, then since I'm keeping the height the same, it's going to have to, I would have had to be closer to it to be able to look up steeper and get the same object. So now if I just add those two together, that AB segment is going to be the sum of them. It's going to be 4,055 feet. All right, much more on these trig applications in class.